Hello everyone, welcome back. This is 7.4, Sum and Difference Formulas for Trigonometric Functions. And, the first thing I want to say is that this is really all the section is, are these three formula. Actually, there's a little more to it. These are, of course, only the sum formulas, but yeah, there's a difference formula for each one as well. But I'm just going to justify this by changing the signs. So everywhere you see a sign, well, let's think of it like this. Remember that sine and cosine are each, odd and even functions respectively. So if we were to make this a minus, then you're basically replacing beta with negative beta. Since cosine of negative beta is still cosine of beta because cosine is even, the first term remains unchanged, but the second term remains changed because sine of negative beta is negative sine of beta, of course, because sine is odd. Similarly, when this is negative, the first term is unaffected because it has cosine of negative beta, if you replace positive beta with negative beta. Since this is sine of beta, when you replace beta with negative beta, a negative pops out, making this a plus. So I'm writing each of those two, alternate scenarios. I'm doing it in blue. The blue's not coming out very well, so I'm going to change that to red real quick. So maybe that comes out a little better. So there's a sign change in the middle when you have the difference formulas. Similarly for tangent, actually, if this is a difference, tangent is odd. So when you have tangent of negative beta, that's negative tangent of beta. Similarly here, tangent of negative beta, negative comes out, so that makes this a positive. So you basically have middle sign changes when you have a difference formula, basically. All right. I really want to prove these. It'll just take too long. But let me say this. It suffices to just prove sine and cosine because, of course, tangent of anything is sine over cosine of that value. So tangent of alpha plus beta is the same as sine of alpha plus beta over cosine of alpha plus beta. And really, if you actually write it out, this equation over this, or this expression over this expression, it's actually pretty simple to get it in this form. In fact, there's not really too much manipulation you have to do. You would actually have to divide by cosine alpha cosine beta because that would make in the first term, these cancel, you just get sine of alpha over cosine of alpha, which is tangent alpha. Here, if you divide by cosine alpha cosine beta, the cosine alphas cancel, and you get sine beta over cosine beta, which is tangent beta. I'm not going to say what the bottom is, but, actually, it's pretty simple to see. Because since we're dividing top and bottom by cosine alpha cosine beta, this first term is 1, and then this clearly becomes that because sine over cosine for each of those arguments, alpha and beta, are tangent. I'm going a little on a tangent, no pun intended, but I'm going a little bit on a digression proving. I may actually do a separate video of proving these formula, but let me just say that again, it suffices to prove sine and cosine because all you really need to do is divide sine by cosine to get the tangent one. And believe it or not, there's actually a really nice way to get from one to the other with just a little bit of a manipulation so you don't have to re-go over the same proof again. The proof is a little involved, so that's why I'm kind of talking about it a little bit. But in this section, we don't need to worry about the proof. I'm just interested in that, of course. I always try to express that when I can, and here's an opportunity. But anyways, really what this section is about is just using these formula. So just to emphasize on that, let me box this so we have an understanding that this is given and we're just using this. All right, so if we wanted to find sine of pi over 12, find the exact value for this example of these trig functions of these angles, what we first have to realize is that how can we write pi of 12 in terms of angles we already know? So pi over 12, you think of the number 1 over 12. So if you know the pi, just think of 1 over 12. Now the angles we know are pi over 4, pi over 6, and pi over 3. And I guess pi over 2 as well. But I'm just going to work with these ones. In fact, if you look at these numbers, I'm not writing pi, I'm just looking at the numbers just to get an idea. If you look at the numbers, 1 over 3 and 1 over 4, notice that when you multiply this top and bottom by 3 and this top and bottom by 4, you get over 12. You get 4 over 12, I guess 4 over 12 this one, and then this would be 3 over 12. And notice, 4 over 12 minus 3 over 12 is indeed 1 over 12. And since this is really this guy, and this one is really this one, just hit everything with a pi and you get this equation here. Pi over 3 minus pi over 4. So there are different ways of verifying that, but that's part of the problem here, is to figure out how we can write the argument in terms of smaller values we already know. And it's hard when it's in radians just because we have fractions. We'll see here when it comes down to degrees, it's a little easier. So it's not a bad idea, if you'd like, convert these into degrees first to get used to it, and then you'll see. In fact, pi over 12 is half of pi over 6. Pi over 6, if you remember, is, well, let me see, pi over 6 is 30 degrees. So pi over 12 would be half of 30 degrees, which is 15 degrees. So since 15 is 60 minus 45 degrees, but also 45 minus 30, there's another way you could have represented this, which would have been okay. But I'll just use this one. So with that being said, we're going to basically use a difference formula. We're going to say this is the same as sine of pi over 3 minus pi over 4. So we're using the difference formula for sine, which is the top one with the red signs. So this is going to be sine of pi over 3 cosine of pi over 4 minus the other way around. So sine of pi over 4 cosine of pi over 3. And we know what these values are. Sine of pi over 3 is radical 3 over 2. Cosine of pi over 4 is radical 2 over 2. Minus, this is radical 2 over 2 for sine of pi over 4, and cosine of pi over 3 is 1 over 2. Perfect. So now this is radical 6 over 2 minus radical 2 over 2. So altogether that's radical 6 minus radical 2 all over 2. And by the way, the phrase exact value just means we want to write it in terms of radicals basically, because otherwise you'd have to approximate and that wouldn't be an exact value. So this exactly represents the value of sine of pi over 12. Perfect. Now for this one, 75, how can we write 75 in terms of the angles we already know? Now remember, the angles we already know in the first quadrant, I guess, would be, well, 30 degrees, 45 degrees, and 60 degrees. 0 and 90 technically are other ones in the first quadrant that we know cosine of, but I'm just going to work with these. And how can we, well, I think it becomes kind of clear. If you just add those together, we're good. So in fact, we can say this is the same as cosine of 30 degrees plus 45 degrees. So this is actually legitimately an addition formula for cosine. So we're going to use cosine of, well, the black signs, alpha plus beta. So this will be cosine 30 degrees, cosine 45 degrees, minus sine of those values. So sine 30, sine 45. And now what we need to do is just evaluate them, of course. Cosine of 30 is radical 3 over 2. Cosine 45 is radical 2 over 2. That's a times. Minus sine of 30 is 1/2. And sine of 45 is radical 2 over 2. And you may be able to tell already, I can tell already, we're going to get the same answer here. And it's no coincidence, and I can actually explain a little bit why we get that same result. Oh, by the way, this is 2 times 2 is 4, so these should have been over 4. My mistake. That would have been bad. Okay. I was going too quick, I guess. All right, so we get the same value. How can we explain that we get the same value? Well, notice sine and cosine are the same when their arguments are a difference of 90 apart. So in other words, this angle on the inside was 15. Sine of 15 is the same as cosine of 90 minus 15 because it's a co-function. And notice 90 minus 15 is indeed 75 degrees. So there was a cleaner way of getting this answer just by realizing that if you convert this to degrees, this is just sine of 15, and cosine of 75 is equal to sine of 15 because those two angles add to 90 as it turns out. But, you know, that's fine. I wanted to show the actual work of using one of the formulas. So again, really that's all this section is. I'm going to do a few more. One we're going to do is an application, well, not an application, but it is a problem that kind of transitions into calculus a little bit. So that'll be interesting to look at. But anyways, I'm going to leave this on the board. I'm going to erase these examples. We'll move on to some more examples right now. Right, so now for this example, this is of course a little more conceptual. We're asked to find cosine of u plus v. We're not given what u and v actually are, but we are given what sine of u and cosine of v are. Now we're also given that u is in the first quadrant, where v is located in the second quadrant. Of course, that explains why cosine is negative. There are actually a few ways you can do this without visualizing things. The best way, honestly, though, is to visualize. So if we kind of consider in the first quadrant, if you draw a triangle in the first quadrant, it'll look something like this. So that's for u. So sine of u is 12 over 13, so this is going to be 12 over 13 like this. And if you use Pythagorean theorem, then this has to be 5. I'm not really going over that too much, but you can verify that on your own. That 5 squared is 25, 12 squared is 144. Adding those together gives you 169, which is actually 13 squared. Also in the second quadrant, the image we'll get will look something like this instead. Because remember that when you're in the second quadrant, the triangle is oriented like this. So I'm not going to write u specifically because, or I'm not going to write v specifically because v would be this whole angle here technically. But if we just consider the sines, then we get something similar. So cosine of this angle would be negative 3 over 5 like this, because again, cosine is adjacent over hypotenuse. And yes, if you consider the triangle 3 blank 5, this has no choice but to be 4. And again, since it's in the second quadrant, technically it's positive 4 distance. So good. So now, just considering this is v, I guess might as well label it. So now we can find, since we completed the right triangles, we can find sine of v and cosine of u. Because, what do we know about cosine of u plus v? Well, it's cosine of u times cosine of v minus sine of u times sine of v. Just like that. Good. And even though I didn't mention it previously with these identities, it is actually true no matter what quadrants you're in. Even if, that's basically what this is illustrating. Even if you have one of the angles that is actually in the second quadrant, when you add them, you'll get something that's probably not in the second quadrant, probably in third or fourth quadrant. But that doesn't matter. These identities hold no matter what. So let's actually see that happen here. So we get cosine of u is, let's see, that's going to be, cosine of u is 5 over 13 times cosine of v is given to be negative 3 over 5 minus sine of u is 12 over 13 and sine of v is positive 4 over 5. There we go, like that. Now they're both gonna have the same denominator, 13 times 5. 13 times 5 is, what's that, 65, yeah? This will be negative 15, this will be negative 48. And when you add those, you get negative, I think that's 63. And I don't think you can, there's no common factor here we can factor out. But we just get this. And what's interesting is that since this is cosine, remember cosine is negative in, well, the second and third quadrants. It's positive in first and fourth by all students take calculus acronym. With that being said, that means since cosine of u plus v is negative, then actually the angle you get when you add u and v together will actually land you in the third quadrant, funny enough. But the question is really just asking for this. So I think we're good there. And like I said, I wanted to do one more example that'll transition nicely into calculus when you see calculus. And it's just a good application of these. So let's take a look at that example right now. Right, so now this problem, like I said, is something that will kind of be seen in calculus a little bit. Basically, this just influences what is known as the derivative of the sine function. And, well, we don't know what that means yet, but in calculus, we'll get a definition for that. And then applying the definition of derivative to sine, you'll basically get this. And there's actually, even though it looks a little funny, there's nice influence, or I guess motivation, for having these two factors here. So sine of h over h and 1 minus cosine of h over h. Those actually approach certain things as h goes to 0, and that'll allow us to find that the derivative of sine is just going to be cosine. But to be quite honest, that's not too far in the future, depending on what classes you take after this, of course. Anyways, moving on. So how do we verify this? We'll work with one side. I want to work with the left side in this case. And the biggest thing that sticks out to me here is that this is sine of x plus h, and we can use the addition formula for sine to expand this out. So doing that, we get sine of x plus h is just sine x cosine h plus the other way around, sine h cosine x minus sine of x all over h. From here we can see that these two actually have sine of x in common. So if you pull sine of x out from those, you get, and we can split it up as well. So let me just write it like this. So we have sine of x outside of cosine of h minus 1. And that's, of course, over h, so I'm splitting up the fraction as that quantity over h, good, plus sine h cosine x over h. This already is good for the first term. This is the same as cosine of x times the quantity sine of h over h. This is actually the same as this one if you swap the negative. So rearranging terms here, the first term, now the first term that was the second term before, is just cosine of x times sine h over h. That's pretty obvious, I think, so not too much to say there. For the second one, though, well, notice this. If we had written negative sine of x, notice since negative times negative is positive, if you distribute a negative into this, you'll get negative cosine plus 1. In other words, you can write this as 1 minus cosine of h all over h. Because if you distribute the negative back in, what do you get? You get negative 1 plus cosine of h, which is exactly cosine of h minus 1. So there we go. We get exactly the right-hand side here. So that wasn't too bad. It was just verifying something, but it at least used the summation formula. So just know the sum and difference formulas come into play beyond just evaluating things, specifically in certain manipulations for other things we need in classes beyond just trigonometry. Well, anyways, with that being said, that's really all I wanted to speak of for 7.4. And notice I didn't really touch tangent at all. So if you want, you can try to verify some tangent values yourself. You can even use your calculator to verify that the values you get are correct algebraically versus with a calculator. That's always a nice thing to do. And with that being said, that ends this video, and I'll see you in the next video for 7.5. Thanks for watching. See you then.